Okay, so I'll still be lecturing by then, so you'll have to look at the, to see the last part of this, you need to look at the video, right? Okay, that's posted. Okay, let's get started because we have some plenty of things that we want to finish today. But looking at the homework list, right? So these homeworks were already due on Monday night, or last night, I mean. And so most people worked on those and finished those, so that's really good. Since it was just due last night, you can still earn credit on that, right? If you work on it through tomorrow, okay? Because you have that 2-day grace period. And then we've got this homework, which is pretty short. That one's pretty straightforward, I think. That one's coming up due tomorrow. And then this homework 5.3, which is due at the time of the test on Monday. Okay, so this is a really short homework. So that you should be able to finish fairly quickly, I think. So I don't want to extend that due date because I want you to also have time, right, before the test on Monday to finish this homework. You need to have that homework finished before the test because these sorts of things are going to be on the test, even though the due date is after the test. And then, of course, working on the sample test, right? So I've been working on the sample test answers, almost finished with them, the solutions. So I'll post those this afternoon. And then when I do that, I'll send an email and put an announcement in my math lab that the sample test 3 answers are posted, okay? So you can use those with the sample test to prepare for Monday. Remember, at the back of the sample test, it says there's several problems that are not going to be on the test that will not be covered to the final, right? So there are problems there, but it says these types of problems will be on the final, but not on test number 3. And those are problems from like these 3 homeworks, right? Okay, so these are ultimately due, but not prior to test number 3. The actual due date, remember I keep telling you this, the actual due date is the day of the final, which is the 9th. But I put the 3rd on there because that's the e-final. So for those of you who have taken the e-final, who are going to take the e-final, it would be best if you had completed these homeworks prior to the e-final, but the actual due date is the 9th. So you can continue working on those without penalty up through the final exam on the 9th. Remember, there are several final exam review sessions. Those are posted in announcements in my math lab. And there is a review also for the final exam, but you've got to finish the test number 3 review first. But there is a review for the final exam. I think I will have that posted also when I post these sample test answers this afternoon. So that's what I'm aiming for. So I'll email about that also. That will go in the usual spot on Blackboard where the sample tests are. That's where the final exam review will be. It's a long final exam review, so it's got quite a few problems on it. But some of those problems we're not going to have on our final. So the problems from the final exam review that are not included on our final, I will tell you which those problems are. So you can just ignore those problems on the review when you're studying for the final. So after the test on Monday, you still got 2 weeks to work on the final. So you got plenty of time there to finish these homeworks and prepare for that final exam. So, of course, you want to take advantage of that time by going to review sessions. And then also, don't forget about just visiting the Math Center in North 925. You can go there at any time and ask questions. So most of you haven't been to the Math Center, so now's a good time to take advantage of that opportunity, okay? Now that you've got, these high-stakes tests, test number 3 and the final exam, coming up back-to-back here, okay? All right, so I think I sort of said everything about what's coming up due, right? Big thing there is just finish this homework and get ready for that test on Monday because you need to do well on that, right? first, okay? Then you can think about tackling the final exam after that. Okay, so do y'all have questions about anything in the process there that's coming up? So we do have quite a few notes to go through today, so we're going to see if we can get through them, all right? Like it's been for the past couple of days, I'm going to have to talk a lot today to show you all these examples. So just bear with me. This will all be on video, so you can go back and look at the video, right? If things are going too fast for you, you can go back and watch the video, okay, and catch up that way. If some things here are not, clear to you when we're going through these ideas. All right, so last time we were talking about exponential functions. Remember, so exponential functions come about when you have a quantity that's growing not at a steady rate, that's linear functions, but quantities that are going at a steady percentage rate, okay? And so whenever you have that situation, most likely, unless there's some other weird condition, most likely that's going to correspond to an exponential function. So remember, in the formula for exponential functions, here's an example of an exponential function. We were talking about this one last time. This is the formula that would give you the amount of radium that remains, the radioactive substance radium that remains from a sample after a given number of, in this case, it's centuries, okay? So radium decays really slowly, so that's why this input here is measured in centuries instead of just years or some shorter time period. But in general, for exponential functions, right, remember you're going to have an initial value, just a coefficient here, and then times a base, and then raised to, and then in that exponent will be your input, okay? So the formulas for exponential functions are really straightforward. They're not complicated formulas at all. Remember, this base is also called the growth factor of the exponential function. And this initial value, that's the coefficient here in this formula, that usually tells you, well, that's the same as the y-intercept of the exponential function. And that will tell you where the exponential function starts, right? So in this case, in this particular problem, that initial value would tell us what the initial amount of radium is in our sample before we start observing it decaying, right? So in this instance, that's going to be 1 gram. So we start with a 1 gram sample of the radium. Now, I wanted to show you here, we kind of mentioned this last time, but I didn't write it down. So this base, again, is also called the growth factor. And if you take that base and subtract 1 from it, that will tell you what the steady percent change is in the outputs. Remember, exponential functions correspond to a steady percent change in the output, right? So take the base, subtract 1, and that will give you the steady percent change. Well, if you convert that number to a percentage. So in this example, the steady percent change here is going to be, well, the base there, which is 0.958, and then we subtract 1 from that. So we get 0.958 minus 1, and notice that comes out to be minus 0.042. And if you convert that to a percentage, that would be negative 4.2%, right? So what that tells us is that this radium is decreasing by, the amount of radium is decreasing by 4.2% every century, because the inputs here are measured in centuries. So see, radium doesn't disappear very quickly, right? Only 4.2% will disappear every century. So, because this steady percentage is negative, of course, right? That means the amount of radium obviously is decreasing, right? It's not increasing. Okay. All right. Well, let's answer a couple of using the formula, right? And the first couple of questions are pretty easy to answer. So I've already answered the first one, in fact. How much radium is initially in the sample, right? Okay, and that corresponds to your initial value, right? Okay, so that's going to be 1 gram. So we have a 1 gram a sample of radium here. Okay, that's actually quite a lot of radium. Of course, the other way you can get that is to just take a formula and plug in 0 for elapsed time, right? Because at elapsed time 0, that's at the beginning, all right? And what's 0.958 raised to the 0th power? When you take a number and raise it to the 0th power, what do you get? 1. So you end up here with just 1 times 1, right, which is, of course, 1. So there's another way, if you want to be more formal about it, of figuring out, oh, I got 1 gram of the radium to start, okay? But see, that 1 gram is not going to remain very long, right, because the radium begins to decay, correct? Slowly, but still, it's going to decay. So, and that's what the formula helps us with, right? So, so the next question, again, pretty straightforward, right? We want to know how much radium is left after 500 years, okay? So that sounds like a long time, but again, for radium, not that long, right? Because it doesn't decay very slowly. All right, so just use your formula, right? And plug into the formula. You would just plug in. I'm not going to write the 1 in front anymore. That's not necessary. So in the formula, you would just plug in, right, the right amount elapsed time for t. Be careful here, though. You do not want to plug in 500, right? That's going to give you a wildly incorrect value. Why? Well, 500 is a huge number, okay, but we're going to do this with our calculator anyway, Arthur, so we can easily raise 0.958 to the 500th power on the calculator, okay? But that's not really the problem here. How are the inputs measured in your formula? In what? Well, it's elapsed time, but it's measured in centuries, right? So you have to be careful of that. So you don't want to plug 500 in there. How many centuries is 500 years? 5, right. So the correct input there is not 500, but 5. So if you plug 500 in there, you're going to get, like I said, a wildly incorrect value. All right, now, the rest of this is just arithmetic. We have to take the 0.958 and raise it to the 5th power, and that's going to require us to use the calculator, all right? So if you have a scientific calculator, you will have some mechanism on that calculator for taking any base and raising it to any power, all right? But it differs slightly from calculator to calculator. So on my calculator, the one I'm using today, here's what I would type. I would type in the 0.958, okay? And then on my calculator, there's a key that says y to the x. But on some calculators, that's x to the y, all right? So I would type in the 0.958 and then hit this key and then hit my input, okay? And that would raise the 0.958 to the 5th power for me, okay? Let me see what that comes out to be, all right? So 0.958, and then I'm hitting the y to the x key, and now I'm going to hit 5 and then equal, and still a pretty big number there. This turns out to be 0.81, okay? I'm rounding off to 2 decimal places, all right? So, look, you need to check on your calculator how to do this, all right? So how to take any base and raise it to any power, okay? Because in using these exponential functions, we frequently are required to do this sort of operation, all right? Just take an arbitrary base and raise it to an arbitrary power. Another thing that you might have, if your calculator is a little bit more advanced, sometimes you will use the caret key, all right, to raise a number to a power. That caret often means exponent, all right? So you may have that on your calculator. So check to make sure that you can do this, all right, that you can raise 0.958 to the 5th power, because otherwise you're going to just have to leave something blank on the test, okay, if you encounter a problem like this one. Let's try going the other direction though, and this is much harder. So here's my question: what is the half-life of radium? So this is an important measure for radioactive substances. Scientists will discuss the half-life of a radioactive substance, and that means how long will it take for the substance to decay by 1/2, all right? So how much will it take for the original amount to go down by 1/2? Well, in this case, we're solving an equation, right? Because we're looking for an amount of time, all right? So you're not going to plug the 1/2 in for t, right? But instead, you are kind of set up this equation to solve for t, so you can find when the amount goes down to 1/2. Why did I put 1/2 here? Because what was the initial amount of radium? How much did we start with? 1 gram, right, okay? So half of that would be 1/2 gram, all right? So I'm going to plug 1/2 gram in for the amount and then try to solve this equation for t. That is now a tricky equation to solve because the t, darn it, is in the exponent. So it's not clear how I'm going to get that t out of the exponent, so I would have a solution to this equation. See, okay? There you have t up in the exponent, but to solve the equation, you need the t out of the exponent, right? So how do we accomplish that? All right, well, okay, that's one of the big things that we're going to talk about today, okay, is how we solve an equation like this one, okay, where our unknown, in this case t, is in the exponent. So how do we get that t out of the exponent so we can write down the solution for the equation? But for the time being, okay, before I show you how we do that, for the time being, we're just going to have to solve this by experimentation, all right? So let's try something. I'm just going to guess here, in other words, all right? Is the t going to be 5? We just tested that, didn't we? Back in the previous example, didn't we test that? When you plug 5 in for t, what do you get for the amount? See, here we plug 5 in for t, right? What do we get for the amount? 0.81. But we want the amount to be what? What? 0.5, right, okay? So the solution is not 5, right? Okay? That's going to be a little bit not long enough, right? Okay? So 500 years is not long enough for this radium to go down by 1/2. All right, so Leslie, what do you suggest we do there? Again, just by experimentation, since 5 is not enough, right? See, we got there that when you raise 0.958 to the 5th power, you get 0.81, right? So what do you want to try? I'm going to try upping the t, okay, because I'm thinking it's going to take a little bit longer. So I just doubled it. I have no idea if that's a good choice or not, okay? So now let's test this. Just going to take 0.958 and raise it to the 10th power, okay, and see what happens. So if you do this on your calculator, if you take 0.958 and raise it to the 10th power, it does come out lower, of course, right? But still not 1/2, right? We end up with 0.65, okay? So the half-life is going to be a little bit longer, right? Okay. What would y'all like to try next there? So this is just trial and error. Just go up to 15, right? Or you can try anything, but that's what I tried, 15, okay? And when you raise it to 15, while you're really close to the answer there, you get 0.958 to the 15th is 0.53. That's almost 0.5, but not quite enough, right? Okay, so it's going to take a little bit longer than 15 centuries. This is 15 centuries. This is 1,500 years. So it's going to take a little bit longer to get that amount of radium down to 1/2. So I just tried 16 because I knew it wasn't going to be much longer. And that works out really nice, okay? When you raise 0.958 to the 16th power, you get not quite, but almost exactly 1/2, all right? I think it's maybe a little bit more than 1/2, but it's really close to 1/2. So there, I think, is our estimated solution to this original equation. The t is going to be about, not exactly, but pretty close to 16, okay? So it takes, the half-life of radium then is 1,600 years. It takes 16 centuries for radium to dissipate by 1/2. That sounds really slow, but and I guess it is really slow, but you still don't want to be next to that 1 gram radium of that 1 gram sample of radium. That is decaying fast enough that if you are near it, I think it's going to harm you. Okay, if you're near it for any extended period of time, that's going to harm you. All right. Well, that's really clumsy, right? Okay, that's not really the way we want to go about solving this equation, because that's that trial and error, right? It only gives us an estimate, and it's really hard, right, to go through that process. So we need to get a more efficient way of solving this equation. But for right now, that's the best we can do. Let's try another example. So here's another place where exponential functions really are frequently applied. This is in population growth, or it could be population decline, but in this case I think it's population growth, okay? All right, so here we have some E. coli bacteria in a culture, right? So E. coli, I think there are different strains of E. coli, and some of them are going to be poisonous, but maybe others are benign, all right? Because, you can get E. coli poisoning from, like vegetables that are not properly clean, right? Okay, so anyway, so we have this experimental culture, right, of this E. coli bacteria, and it says that the number of bacteria can be modeled by this function, all right? And that looks like an exponential function, right? Okay, because see, notice there you have your t in the exponent, right, of this base with an initial value there, right? Okay. This base is a little bit unusual, though, right, because it involves that irrational number e, right, that we discussed before. Remember, e is approximately 2.71828, but it's an irrational number, so it doesn't terminate and it doesn't repeat. Okay, so what's our initial value here? $500,000, right, okay? The initial value is 500,000. That's just the coefficient, right, of our power here, okay? So initial value is 500,000. That means then that there were, I don't know how they count the bacteria, but that means that there were 500,000 bacteria, right? It's probably by weight that they count. So that means there were 500,000 bacteria, right, in the sample initially, okay, or in the culture initially. The growth factor here is a little bit tricky, though. The growth factor, remember, that's the base of the exponential function, but the growth factor is not e, okay, because of this coefficient here on the t. So actually, to find the growth factor, what you have to do is raise e to the 0.014. That will be the actual growth factor here. What is e to the 0.014 power? Well, that's another thing that, of course, you'll need to do with your calculator, right? So another thing that you need to practice with when you're doing the homework is how to raise e to a power on your calculator. And again, that differs from calculator to calculator. But on many basic scientific calculators, if you look at the second function or the shift of the ln key, every scientific calculator will have an ln key on it. That often is e to the x key, all right? So you can use that key to raise e to a power. I think the way you do that is just type in your power and then hit that e to the x key, okay? And it will compute e to the x. This turns out to be very close to 1, but not 1. It's approximately 1.014, okay? That is the actual growth factor or base for this exponential function. So what's the steady percent change here? How fast is this culture growing, if that's the base? How do you find the steady percent change? We mentioned that a moment ago. Montel, you must be just absorbing all of this just through your eidetic memory, right? Okay, because you're not writing anything, all right? So that's amazing. Really surprised by that. So how do we get a steady percent change here? It's b minus 1, right, okay? So just take the b, which is we've calculated as 1.014, and then subtract 1 from it. But, of course, now you have to convert that to a percent. So what is 0.14 there as a percent? Yeah, 1.4%. Notice that comes out to be kind of close to this coefficient here. Sometimes students think they're exactly the same, but they're not quite, all right? They're not quite identical. So this culture is growing. The population is growing, but it's not growing very rapidly. Depends on how you think of it. It's growing by 1.4% per what? Per what? How are we measuring elapsed time here? Minutes. So I guess that could be fast, right? It's growing 1.4%. That seems like a low percentage growth rate, but it's per minute, okay? So I guess it really is growing quickly, all right? Just in 1 minute, you've already gained 1.4% extra bacteria. So how many bacteria are present after 99 minutes? That's the easy thing to calculate, right? You're just going to plug 99 into the formula and do the computations. So you need you'll need a calculator for this, right? Because you're going to take 99 and then multiply it by the 0.014. And then you have to raise e to that power. So that's 500,000 times e to, what's 0.14 times 99 there? $1.386. This is 1.386. So you have to raise e to the 1.386 power and then multiply it by 500,000. Okay. All right. So let me see if I can do that. So I've got the 1.386 on the calculator. My e to the x key is my shift of my ln key. So that comes out to be close to 4, but not quite 4. And then I'm going to multiply that by this big coefficient, this big initial value, 500,000. Wow, what does that turn out to be? Got to write that down. 1, and then 3 9s, and then 411, and then, I don't know if the decimal points really matter here, but 0.36, okay? So that means we have 1,999,411 bacteria. Okay, I don't think the 0.36 counts there. All right. So almost, right, after 99 minutes there, almost 2 million bacteria, right? So that culture in a little over an hour and a half, right, 99 minutes, has already quadrupled. It went from 500,000 to almost 2 million, right? Okay, so that population is really growing rapidly. Oh, I think that's why. I think that's probably gives you an idea of why why you don't want to get infected with E. coli. All right, because in your gut it's going to reproduce really quickly, and so it'll make you sick fast. All right, you're going to get sick really rapidly from exposure to E. coli. All right, now we're back to this question. And this is the question we had a hard time answering in the previous question. So how long will it take? How many minutes is it going to take for the population to go up to 25 million? So it starts at 500,000. How long will it take to get to 25 million? So that means we got to solve an equation because we're going to plug in the 25 million for the population. That's the output. So that goes on the left-hand side of the equation. And then, of course, on the right-hand side is the formula, which I left off part of that. So the formula is 500,000 e to the 0.014t. So we have to figure out now how to solve this equation. And again, the hard thing about that is the unknown that we're solving for t is in this exponent. But to solve the equation, we have to get t out of the exponent, right? So that's not an easy thing to do, okay? How to get the t out of the exponent so we'll know what the solution to the equation is. So we can try to do that by experimentation, okay? So you can experiment with some different values for t and see if you can find one that gives you a population close to 25 million. So you just have to use your calculator and do a little trial and error, right, okay, to find approximately what t is going to be. But, again, that's clumsy, right? So that could take a long time. So now we want to develop a faster way of solving this equation, okay? And the key is going to be the idea of inverse functions. So we're going to use a kind of a technique to solve this equation that's much different from the algebraic techniques that we've been using, like the quadratic formula or factoring, to solve equations up until now, okay? This is a little bit more sophisticated idea for solving equations. All right, so we got to introduce some inverses here. Okay, so you know, right, that if you have an exponential function, right, and if the initial value is 1, then you get an exponential function formula that looks like this, right? That's if the initial value here multiplied in, this coefficient is 1, okay? So I'm looking at kind of a restricted type of exponential function, an exponential function where the initial value is 1, okay? It turns out that these types of exponential functions where the initial value is 1, okay, these functions have inverses, all right? So these functions have inverses, and so every exponential function of this type, no matter what the base is, so the base can be any number here as long as it's positive and not equal to 1, exponential functions of this type, again, where remember the initial value has to be 1 though, okay? Those exponential functions have inverses. And these inverses have a special name. These are called logarithmic functions or logarithms. So you've probably heard the term logarithm, you know, because that term comes up frequently, or not frequently, but sometimes in, you know, just casual usage, okay? And this is what logarithms mean. They are inverses of exponential functions. Remember, though, the initial value here has to be 1, okay? The initial value has to be 1. So let me show you how we denote logarithmic functions, okay? We have a special notation for them. So log functions, we just give them the name log, okay? So we just shorten the word logarithm, right, down to just log. But remember, you have a different exponential function for every different base, okay? So, so to indicate what the base of the logarithm is, you put that as a subscript beneath the log, okay? So the key thing to remember here is this function, log base b of x, that's the name of the function, log base b, that's how you read that, by the way, is log base b. Remember, that is the inverse of the corresponding exponential function, which looks like this, okay? So these two functions are inverses of one another. By the way, how do you test if two functions are inverses of one another? Remember, what was our test for that? So how do we check to see if two functions are inverses? What do you do? There's a test for this. Well, there's a problem like this on the sample test, so this is probably going to show up on test number 3, okay? You test to see if two functions are inverses of one another by composing them. You compose them, and what are you supposed to get if they're inverses? X, right. So, because these two functions are guaranteed to be inverses of one another, when you compose them, you're going to get X. That's a really important fact, all right? So when you take a log function and compose it with its corresponding exponential function, the base has to be the same, by the way, okay? The base must be the same, all right? When you compose those two functions, they're going to cancel each other, and you're just going to get X. We're going to use that idea, we're going to exploit that idea a lot here in just a second, all right? But keep that in mind. This is this function that I call log base b of x. That is the inverse of this exponential function. Of course, if you change the base, you get a different exponential function, and you get then a different logarithmic function also. So in the notes here, I just wanted to emphasize that log functions and exponential functions are inverses of one another. So when you compose them, you have to get x. So if you take the exponential function b to the x, and if you input that to the log base b function, in other words, if you compose these two functions, these things will cancel each other, and you'll just get x. And the opposite is true also. If you take the log function and input that to the exponential function, that's what I'm doing right here. I'm taking the log function and I'm inputting it to the exponential function. These two things, again, will cancel each other, and you'll just get x out of that, okay? That you're guaranteed. You're guaranteed. But you have to make sure that the bases are the same, okay? So the bases have to be the identical. That's how log functions come about, just inverses of exponential functions. Now, log functions are functions. They're functions, so they have properties like other types of functions do. And the two key properties that I want to stress to start with here are these two. These you have to keep in mind. First, let's talk about the domain. See, log function has a domain, but the domain does not turn out to be all real numbers. So you cannot plug any number that you want into a log function. The domain is only positive numbers. So that's sometimes important. You have to keep that in mind. All right, so domain only positive numbers. And here is the other really important property, okay? Because you know, log functions are functions, so we need to be able to evaluate them, right? We need to be able to plug an input here and figure out what the matching output is. Here's how you do that, okay? Now, Actually, the main way we're going to do this is with our calculator, okay? Because calculators are good at evaluating log functions, all right? But by hand, here's how you can evaluate a log function. You do not have a formula for log functions. Log functions do not have formulas. So that freaks students out sometimes. Log functions don't have formulas, but here's how you can evaluate a log function. And this is it. If y is equal to the log of x, then that means if you take the base and raise it to the y power, you're going to get x. All right? So look at that really carefully. Suppose we know this is true. Y is log base b of x. So when we plug x into this log function, suppose we get y as our output. What that means is if you take the base and raise it to the y power, you're going to get x. The reason that's true, I'm not going to demonstrate for you, but the reason that is true has to do with the fact that these two functions are inverses of one another, okay? All right, now, you're going to look at that and say, how am I going to use that? How does that property help me evaluate log functions? Well, I'm going to show you right now, because we're going to evaluate some log functions. Here's a very important log function. It's not the most important, but it's one of our favorite log functions, log base 2, okay? Log base 2. Keep in mind, that is the inverse function. That's the inverse function of y equals 2 to the x. These two functions are inverses of one another. But, okay, that's great. How am I going to now evaluate, though, log base 2 of 4? What is log base 2 of 4 equal to? Right? By the way, you can put parentheses around the 4 because that's the input to the function. But sometimes in log notation, we leave off the parentheses, okay? So you might see parentheses written around the input or you might not. All right, so how do I figure out what log base 2 of 4 is equal to? All right, here's what you do, okay? That's equal to something, right? I hope. So let's call that y, all right? Until I figure out what y is, I'm just going to call that y. All right, now, what do I know about y? If you take the base and raise it to the y power, what do you have to get? That's this important property, okay? So see, I had y is log base 2 of 4, right? So what that means is if you take 2 and raise it to the y power, what do you have to get? This number, all right? So let's apply that to this situation, all right? So if I take 2 and raise it to the y power, I'm supposed to get 4. Now, looking at this equation, can you just figure out what y has to be? 2, right, okay? So log base 2 of 4 is 2. That's how you evaluate log functions, okay? So you have to do a little bit of inspection there, all right? Because there's not just a formula you can plug the 4 into and do some arithmetic and get this answer, okay? You have to think about it in this kind of indirect way. Yeah, Montel, what were you questioning? All right, Montel, so let's try this one, log base 3 of 9. So this is the name of the function. Every time you change the base, you get a different log function. So you have lots and lots of log functions, right? This is the name of the function. This is like f. All right, and this is the input, okay? All right, so we're trying to figure out here what is, in other words, something like f of 9, right? We're trying to evaluate this function notation. So what's my scheme for doing that? You know, think of it like this, Montel. So what did I say? Yeah, first I said, okay, I'm going to call this y, all right? But now what do I know about y? Y is the exponent, right. So if you take 3 and raise it to the y power, what are you supposed to get here? 9. Now you just have to look at this equation and figure that out. So what's y equal to? What power of 3 gives you 9? 2, right, okay. 3 squared is 9, correct? Okay, right? So log base 3 of 9 is 2, all right? If you plug 9 into the log base 3 function, the matching output is 2. All right, so we have to practice this quite a bit or we're not going to get it down. So I have lots of examples here, but I'm going to do them all the same way. All right, well, no, not all of them the same way, but mostly the same way. So let's try this. Log base 4 of 64. That's how you read that. Log base 4 of, it's of because this is input, right? Log base 4 of 64. So after a while, you'll be able to do this without writing down the y, but let's take it slowly here. So I'm going to call that y, and what do I know about y? If you take 4 and raise it to the y power, you're supposed to get 64. So what's y equal to? What power of 4 is 64? Cube, right, okay, it's 3. 4 cubed is equal to 64. 4 times 4 times 4 is 64. So log base 4 of 64 is 3. What about log base 5 of 625, right? So I'm going to call that y, and what I know is if I take 5 and raise it to the y power, I get 625. So you may have to experiment with this a little bit. What power of... It's fourth power, right, okay? So 5 to the fourth power is 625. Just check it on your calculator. Log base 2 now, that's called the binary log, okay? So that has a special name. That's called the binary log. So that's a very important log function, base 2. And the reason is, digital information is stored as base 2 numbers, okay? That's how digital information is created. So, almost all the information now that you interact with is digital information. That's why log base 2 is important, okay? Its base is also 2. So here we're trying to find the binary log of 1/2. All right, so binary log of 1/2. So this one you have to think a little bit more carefully about. 2 to the y power is 1/2. So what power of y gives you 1/2? So this is where your knowledge of exponents is really going to help you. It's -1. -1. Why? Because 2 to the -1 power, what does it mean to raise a number to the -1 power? It means take the reciprocal, right? So that is 1 over 2 to the first power. So in working with logs, this is where it's really going to exploit your knowledge of exponents, all right? So I've been trying to yell at you about that all semester, right? It's important to know about negative exponents and fractional exponents as well, okay? What about log base 3? Now, log base 3 is not really an important log, okay, right? But it's a good example. What about log base 3 of 1/27th? So, again, you're going to call that y, and then you're just going to think here, 3 to the y power is 1/27th. So can we figure that out by inspection? What power of y? What power of 3 gives us 1 over 27? I think it's going to be a negative number, right? Okay. Because if that were a positive number, I think not going to work, right? So I think y is negative. What negative number there? Is it -1? What's 3 to the -1 power? Nope, not -3. No, negative exponents do not give you negative signs. All right. So what's 3 to the -1 power? We just did it up here. So, but Y'all got to say it for me. What? 1 over 3, right. So that's not 1/27th, right? What about 3 to the minus 2 power? What would that be then? 1 over 9, right. That's 1 over 3 squared. So that's not it. What about 3 to the minus 3? Yeah, that's 1 over 3 cubed. And indeed, that is 1/27th. Oh, so there it is. Y is minus 3. See, we could figure that one out. This one's also pretty easy. What's log base 8 of 1/64th? So 8 to the y power gives us 1/64th. What's y then? What power of 8 is 1/64th? Well, look at the 64. What power of 8 is 64? Right. 64 is 8 squared, correct? But we want 1/64th, so you would use 8 to the minus 2 power, right? That would be 1 over 8 squared, which is 1/64th. So the answer here is minus 2. Don't forget about fractional exponents. I'm giving you a hint here. What is log base 16 of 4? Log base 16 of 4. By the way, the domain, remember I said the domain of the log functions is any positive real number. So you can plug any positive real number. You can't plug 0 in, though, or negative, but any positive real number you can plug into a log function. So all of these values exist. That doesn't mean they're easy to find, but they all exist, okay? Well, let's see if we can find this one. Log base 16 of 4. So that means if you take 16 and raise it to the y power, you're going to get 4. My goodness, what could that be? 1/2. Great, right. That is 1/2. 16 to the 1/2 power is the square root of 16. That's what I was yelling about y'all last time, okay? All right. 1/2 power means square root. So square root of 16 is 4. So here it's 1/2, okay? What about log base 8 of 2? So 8 to what power gives us 2? So is there a power of 8? There is, but is there an easy power of 8 that is going to be 2? What? 1/3, right. Okay, see, Arthur's got the hang of it now. It's 1/3. Because what root does 1/3 exponent correspond to? Cube root, right. Okay. 8 to the 1/3 power means the cube root. Cube root of 8 is indeed 2. 2 times 2 times 2 is 8. Yeah, so what if this were 8 to the minus 1/3 power? What is 8 to the minus 1/3 power? That would be 1 over 8 to the 1/3 power. So that would be 1 over 2. Okay. Remember, negatives just give you reciprocals. Fractionals give you radicals. Maybe we need that here. What's log base 16 of 2? So, again, we're asking now, what power of 16 is 2? So 16 to what power gives you 2? Is it 1/2? What's 16 to the 1/2 power? We did that a moment ago, right? That's 4. Oh, it's 1/4. Yeah, it's 1/4. Because 1/4 exponent means 4th root. 4th root of 16 is 2. Because 2 times 2 times 2 times 2 is 16. Yeah. What now?
So to get 16, raise 2 to the power of 4, right?
So I see you're thinking of, but then you have to take 4th root of that, right? I mean, I guess that's correct, but be careful with that, okay? All right. Now, we don't often work with log base 16 or log base 8. The most frequently occurring logs are log base 10 and log base e, strangely enough, okay? Log base e. Again, e is that weird irrational number. So it's a little bit unusual as to why log base e is so crucial. It's kind of more clear about log base 10, right? Because our number system is base 10. Log base 10 is referred to as common log. All right. So binary log is base 2. Common log is base 10. All right. If you're computing a common log, you can just leave off the base. That's understood to be base 10. Okay, so if you see the word log without a base, that means usually log base 10. There are some exceptions to that, but on your calculator, that will be log base 10. Every scientific calculator will have a log key, an log key on it. That means log base 10. What's log base 10 of 100? We don't need a calculator to compute this, but you can do it with your calculator. Right, this means 10, right, to what power gives us 100, and the answer there is 2, right? Okay, so this is 2. 10 squared is 100. So this also is common log, all right, because I've left off the base. So what's log of 1/100th? I think, again, we can just figure that out. 10 to what power gives us 1 over 100? Well, 10 to the second power is 100, right? So how do we get 1 over 100? How do you get reciprocal? Negative, right. So this would be 10 to the minus 2 power, right? That means 1 over 10 squared. That would be 1/100th. So the answer here is -2. Okay, now usually you're not computing logs of these easy values, right? Okay, where you can figure them out by inspection. Usually we're not that lucky. So here's an example of that, log of 75, right? So what we're asking for here is something we're not going to be able to figure out by inspection, because what I'm asking for is what power of 10 is 75? I have no idea, okay, right? Well, I have a little bit of an idea. It's somewhere between 1 and 2, right? Somewhere between 1 and 2, because 10 to the first power is 10, but 10 squared is already what? 100. So y is somewhere between 1 and 2, but I don't know what that is, okay? That's going to be some probably irrational value between 1 and 10, so, between 1 and 2. So you need your calculator here, all right? This is, we're going to have to do this with a calculator. So, but your calculator will do this really nicely. Just type in 75 and then the log key, or maybe log and then the 75, and what do you get there for that? So 75 and then my log key 1.875. That's to 3 decimal places, okay? You'll usually get an infinite number of decimal places, so you're going to have to round off somewhere. Usually 2 or 3 is plenty, all right, for my purposes. So log base, common log of 75 is about 1.875. Again, what that means is if you take 10 and raise it to the 1.875 power, you will get approximately, not exactly because we rounded off, but you will get very close to 75, okay? What about log of 0? I'm trying to trick you here. So what's common log of 0? This is a trick question. What's common log of 0? What? It doesn't exist, right? Okay. This is undefined. Because remember, the domain of log functions, any log function, is only positive numbers. This is 0 is not a positive number, though, so this is undefined. If you try this on your calculator, compute log of 0 to give you error. All right, it's going to give you an error there. Here's the other important log base, base e. This is called the natural log. Now, you may wonder, what is natural about using a base of e, because that's a really strange number, right? Actually, though, log base e was developed before log base 10. The first log base that was used in calculations was log base e, all right? And that was developed in the 1500s and around the 1500s, and very early in just as part of the Renaissance. And that really, the development of the log function, that really revolutionized European mathematics. That was a big step forward. Before the development of the natural log function, that popularized the use of decimals in Europe. Before the natural log function came into use, people knew about decimals, but they didn't use them very much. But after that, decimals were used a lot more. The natural log function. I'd have to look and see how I forgot the name of the Napier is the guy who's responsible for this. I'm not exactly sure what his primary application was, but logs were frequently used to aid in computations because remember there were no calculators. All right, so logs were for various reasons are very useful in doing complex arithmetic calculations. You may wonder, how is that possible? But they are, okay? And that's how they were first applied. So that people could do arithmetic, this is in the pre-calculator era, all right? Yeah, and there are ways that you can do this, but we're not going to show those because that's not an important application anymore, right? All right, so what about natural log of 1? Oh, by the way, the abbreviation for a log base e is ln. So on your calculator, you're going to have an ln key. And so you can compute this with your calculator, natural log of 1. But you can do this also by hand because it works the same way as all other logs. Natural log of 1 means that if you take e and raise it to the y power, you're supposed to get 1. What power of e will give you 1? 0. That's right. So this is 0, right? Because e, like any other number raised to the 0th power, is going to give you 1. What about natural log of e itself? So suppose the base is e here, but suppose you input e to the natural log function. So what's the natural log of e? Well, let's see. What power of e gives us e? That's what we're asking there, natural log of e. What power of e gives you e? That should be easy, right? What is it? So what do you have to raise e to get itself? What? 1, right, okay. So this answer is just 1, okay. Natural log of e itself is going to be 1 because e to the first power obviously is e, right? But most of the time you cannot evaluate the natural log function by hand, okay, right? So you're going to have to rely on your calculator. Let's see what natural log of 75 is. So what does the calculator tell us for natural log of 75? That's approximately what? Yeah, 4.317 to 3 decimal places. That's the natural log of 75. That means if you take e and raise it to the 4.317, you will approximately get 75. Okay, we rounded off a little bit, so you won't get exactly 75, but really close to 75. Okay. And finally, one more trick question here. What's natural log of -2? So you can try this on your calculator. What does your calculator say? Yeah, it's error, right? Okay, because remember, the domain of natural log functions has to be positive, right? Okay, so this is undefined. You can't calculate natural log of negative number. There is no power of e that will give you a negative result. No power of e will give you -2. That's why this is undefined. This is a very easy exercise. We don't have to do any calculations, but you have problems like this in your homework. It says, take this equation and put it in log form. So how would we take this equation and write it as a log? So I have 7 to the 3rd power is equal to 243. How would I write that as a log? So you write log, what would be the base? 7 of what? 343, and that's equal to 3, right, okay. What about this one? Square root of 36 is 6. That's true, right? Okay, we do know square root of 36 is 6. So log of what, though? What's the base? Not 6. Remember, it's this number that's... So it's log base 36 of 6 is equal to 1/2. Wow, where did that come from? Square root, right. This, remember, square root means the same as 36 to the 1/2 power. Now it looks like this, right? Now this equation looks like this one. So we would write this as log base 36 of 6 is equal to 1/2. What if you go the other direction? So how do you write this as an exponent? There you have a log. How do you write that as an exponent? What's the base here? 10, because it's not written. So how do you convert that to exponential form? What is that telling us? The fact that log base 10 of 1,000 is equal to 3, what does that tell us? 10 to what? The power of 3 is 1,000 exactly. What is this telling us? This is natural log. So what's the base here? E. So what's this telling us about E? What is that equation telling us about E? It's going to be E to something, right? What power? What did we do here? We took 10, raised it to this power, and got this, right? So here we're going to take E, raise it to this power, 4.605, and that should give us 100. Okay. So that equation, that log equation there, is just another way of telling us E to the 4.605 power is 100. Okay. Those two equations are equivalent to each other. All right. Now, why did I go through why did we go through this process of explaining about these log functions? Okay. Why are they on your calculator? Right. Okay. So why are they important? Well, remember I said we're going to use these log functions. They're inverses, so we're going to use them to help us solve equations. That's what we're getting ready to do. Okay. All right. So let's take a break here for a few minutes, and then we're going to come back and I'm going to show you how to solve equations with log functions. You'll like it because it's pretty easy. All right. And the calculator makes it especially easy. The test is Monday, right? Okay. But remember, this material is not on the test 3. This will be on the final exam, however. Okay, right? So test number 3 only goes up through homework 5.1. I think 5.1. No, 5. I forgot. The one that's due on I think it's 5.3 actually. The one that's due on Monday is the last homework that's on the test. So that does not include what we're talking about today. Did you want this on the test? Oh, got to resume there. That's too bad. So we missed that example. But that's okay. The next example is very simple. Very similar, I mean, right? So now I have e to the x power is 55, okay? All right, I want to solve that equation. So you see it's exactly the same problem. I've got to get the x out of the exponent, right? Okay? But again, if you look at the left-hand side here, right, that is just an exponential function. The base is e, okay? Right? What is its inverse? Natural log, log base e, right? That's natural log. So I'm going to apply the natural log, log base e, to both sides of the equation. And because these are inverses, this very conveniently cancels on the left-hand side to just be plain x. And then on the right-hand side, I need my calculator, right? So I'm going to use my calculator to estimate natural log of 55, right? So what does the calculator say natural log of 55 is? Yeah, 4.01 if you round off to a couple of decimal places there. So there's our solution to the equation, right? X is about 4.01. See, now you've gotten the hang of it, right? So how are we going to solve this equation? 10 to the x minus 2 is 200, right? So what will we apply to both sides of that equation? What function? Log, right. Log base 10, which is common log. That's log. So I'm going to apply the common log to both sides of that equation. So I have log of 10 to the x minus 2 is equal to log is log base 10, right, of 200. And now the left-hand side is really easy, right? Those inverses cancel each other. So you just get x minus 2 is equal to log of 200. And so I guess that means that x is 2 plus the log of 200. There's your exact solution, by the way. That's the exact solution. But usually you want a decimal approximation. But this is the exact solution to that original equation. 2 plus the common log of 200. What's that approximately equal to? 2 point, what's that? 2 point what? 2.23. Yeah, so you have 2 plus, and then log of 200 is about 2.23. So you get 4.23 approximately for the solution to that equation. See, so it's kind of very nice and straightforward, right? This one is similarly easy. It's base e instead of base 10. Okay, so this would so we're going to use natural log to solve this equation. But let me show you one. There's one extra step you have to do here. You cannot have a coefficient other than 1 here on the left-hand side, okay? So you've got to get rid of the 4 before you can apply natural log, all right? So how do we get rid of the 4 from that right-hand side, from that left-hand side, I mean, what? Yeah, divide by 4. So step 1 in this equation is you're not going to just immediately apply natural log. First, divide by 4, and then there the 4's divide out, so you get e to the 5 minus 2x is equal to 50. All right. Now you're prepared. So now you can apply natural log to both sides. And on the left-hand side, it's very easy. The natural log and the e will cancel each other. So you get 5 minus 2x is natural log of 50. Now we have to solve for x still, but at least, see, the x is out of the exponent, right? So now we can solve this just using algebra. Let's see, I think I would subtract 5 from both sides. So I get something like natural log of 50 minus 5. And then divide by minus 2, right? So I get x is natural log of 50, subtract 5, divide by minus 2. There's the exact solution. And again, you can use your calculator, right, to get an estimate by using your calculator to estimate natural log of 50. So estimate the natural log of 50 with your calculator, subtract 5, divide that by minus 2, and that will be your approximate solution for x. But that's the exact solution. All right, now this equation we had just a moment ago, right? So now we are prepared to solve it because we wanted to know how long this was the equation we were using to determine how long it took the bacteria culture, which started with 500,000 bacteria, how long it took to get to 25 million bacteria in the culture, right? So we didn't want to solve that equation by trial and error a moment ago. But now we don't have to use trial and error. Now we can solve it with our knowledge of logarithms, okay? So let's try solving this equation. So what do I want to do first here? Eventually, I'm going to apply natural log to both sides, all right? But I can't do that immediately. Yeah, I've got to get rid of this coefficient, okay? So you need to turn that into just 1 times e, okay? So divide out 500,000 from both sides. So that's kind of a big number, but that divides nicely, I think, maybe, into 25 million. What does that turn out to be, 50? So we have 50 is e to the 0.014t. Now you're in great shape, right? Now you can apply the inverse, right, which is the natural log, because this is log base e. So take natural log of 50 and natural log of e to the 0.14t. And these things cancel each other. So we have natural log of 50 is 0.014t, and then just divide both sides by the 0.014. So that's what t is equal to, natural log of 50 over 0.014. What is that approximately, though? Because I really need to know how many minutes, right, it takes for that population to reach 50 million. So what is natural log of 50 divided by 0.014? That's easy to do with the calculator, right? You're going to have natural log key on your calculator, so compute that and then divide by the 0.014, and 279 something approximately minutes. 279.4 actually minutes there, okay? So that's not long. That's what, 4.5 hours, something like that? Yeah, okay. Now, you can go the other direction as well. So sometimes we have to solve equations that have logs in them, all right, instead of equations that have exponential expressions in them. Sometimes we have to solve equations with logs, but you can use exactly the same idea. So here we have log of x. That means log base 10 of x is equal to 3. So again, we've got to solve for x. That means we've got to get the x out of the log, right? Because you ultimately want to end up with, just x equal to some quantity, right? So you've got to get the x out of the log. So the question is, how do we cancel the log, right? So what is the inverse of the log function? Log base 10 function? To the x power, right? So what you'll do here is take both sides of the equation and raise 10 to both sides, okay? Take 10 to the log x, and then also take 10 to the third power. This is the same as composing a function with its inverse, because log base 10 and 10 to a power are inverses of one another. So what happens here on the left by design? Cancels, right? These things cancel, and you just get x. So there's your solution. X is 10 to the third power, which of course is 1,000. All right? You might have been able to figure that one out by inspection, just looking at that. Log base 10 of x equal 3. What? If I raise 10 to the third power, what does that give me? Oh, that gives me 1,000, right? Here's one that you couldn't really solve by inspection, though. So 7 times the natural log of x is equal to 1. And I want to solve again. I've got to get x by itself out of the natural log, right? To know what the solution here is. All right, so again, there's one extra step in this equation. I need to get rid of this coefficient. So I need to have by itself on the left-hand side just natural log of x. So how do you get rid of that coefficient? Yeah, divide both sides by 7, right? So you get natural log of x is equal to 1/7. Now you're in great shape, right? Okay, because what's the inverse of the natural log function? E, right. So take E and raise it to both sides of this equation. And these things will cancel, and you get x is e to the 1/7 power, and you can estimate that with your calculator, all right? Because on your calculator, you have the ability to raise e to a power. It's often the second function of the natural log key, and you can see why that's the case, right? Because natural log and raising e to a power are inverse operations. What is e to the 1/7 power? About 1.15? No, that's bigger than I thought. So 1.15. Neat. All right, I'm going to show you just a couple of other equations here, because sometimes sometimes you'll be solving equations where the base is not 10 or e, all right? So look at this one. So 7 to the x is equal to 12, all right? So see, there's an exponential equation, right? I have an exponential function on the right-hand side, on the left-hand side, right? So, and again, you want to get the x out of the exponent. So we're going to have to apply an inverse, right? So what's the inverse of 7 to the x power? Log base 7, right, okay. So what you would do is apply log base 7 to both sides here. But the problem with log base 7 is that's not on your calculator, right? So this will cancel like before, and you'll get x is log base 7 of 12. And that's great. That's the solution. But who knows what log base 7 of 12 is, right? I have no idea. And you can't get that immediately out of your calculator, most calculators, because they only have two bases, right? They have log base 10 and log base e. So that's not a very satisfying solution. I mean, that is a solution, but that's not a very satisfying solution to the equation, because I don't know approximately what this number is, right? And the calculator may not help me with figuring out what that number is. All right, let me show you, however, what you can do. All right, you can go ahead and use log base 10 or natural log. You can use them. So instead of applying log base 7 to both sides, I'm going to apply natural log to both sides. So this is not going to come out to be x, okay, on the left-hand side, because these two functions are not inverses of one another, right? So they do not cancel each other. These cancel because they're inverses. But this is log base e, so it will not cancel the 7. But it almost cancels the 7, okay? So it gets really close. Here's what you get on the, here's what you really get on the left-hand side. You get x times the natural log of 7. So it's not quite x, but it's just a multiple of x. It's x times natural log of 7. Of course, what do you have on the right-hand side? Yeah, you just had natural log of 12, right? Which you can get out of your calculator, right? Now, how do we finish solving for x here? Divide both sides by natural log of 7. Sure, right. So there we get x is natural log of 12 over natural log of 7. There's your approximate solution. And both of those values you can get with your calculator. Let's try that here also, okay? One more example before we stop here. We had this equation a moment ago, remember? Right? That's where we were trying to find the half-life of radium, and we got the solution to be about 1600, but we did that by guesswork. So let's not do that by guesswork now. Let's do that with the calculator. All right. So see, here we have an exponential function, right? But unfortunately, on the right-hand side, this is an exponential function. But unfortunately, the base is not You know, the base is this really inconvenient number, 0.958, right? Okay. So I am going to use a log function to solve this, but I'm not going to use log base 0.958 because that's really a weird base, all right? But you don't have to use log base 0.958. You can use natural log. You can use natural log. So let's use natural log. So I'm going to take the natural log here of 0.958 to the t power is natural log of 1/2. And now what happens to the left-hand side? Well, the left-hand side is natural log of 1/2, so I can get that out of my calculator, right? But what happens to the right side? These things do not cancel each other, right? Because they don't have the same base, but they almost cancel each other. You do get t, but then you have to multiply in something. What's the something we multiplied in up here? See, here we had 7 to the x power. We took natural log. We did get x, but we had to multiply in what? Of this, right? So you have to do the same thing here, okay? You have to multiply in natural log of 0.958, whatever that value is. So what's my ultimate answer here? T is what? It's the natural log of 1/2 divided by the natural log of 0.958, both of which you can get out of your calculator. Wow, what is that? So what did it come out to be? Oh, 16.15? That's what we got before, right? Okay. That's Aaron Lawrence. What does Aaron Lawrence want? So that's 16.15. That was approximately the answer we got last time, right? We got 1600 years, 16 centuries, right? So we were off by a little bit, but we were close, right? Our guesswork was close there, okay? Neat, all right. So you can solve equations with other bases also still by using natural log, or you can use the common log function. Now, fortunately, those other bases, though, don't occur that frequently. So most exponential functions are going to be expressed with base e. That is by far the most commonly occurring exponential function, with base of e. All right? For various reasons, that's really convenient. All right? So you'll often see base e, and then the inverse of base e is natural log. So you can solve such equations easily, right? Okay. Well, we're done. There's no more to do. If you want more, you have to pay extra. All right? Okay, so the test is Monday. I've told you everything about that I can tell you. So I'll post the sample test answers later today sometime. So be looking for that. They'll be in the usual spot on the Blackboard page. All right? Bye.